So, the title of this workshop is Quantum Physics and Logic, but let's say that the motivation for this particular work comes from logic, and in particular from proof theory. So since I don't assume all of you are familiar with multiplicative linear logic, I will try to give a very short, let's say, crash course on this about this logic. But actually it's going to be quite simple, because the logic itself is not so complicated after all. So, actually, the multiplicative linear logic is arguably the simplest fragment of linear logic as introduced by Girard in 87. The syntax of formulae and rules are as follows. If you look at formulas, they are just atoms or coatoms. The only binary connectives are form of conjunction here, called the tensor, and the form of disjunction called R. And negation, even if it's strictly speaking it's only defined on atoms, can be extended, distributed like in the Morgan style to the full language, as you can expect, letting disjunction and conjunction be the dual of each other. The rules are just four. So there are just four rules. An axiom saying that you can conclude, you can say that A bottom and A themselves are provable sequence. And then there are rules for disjunction and a rule for conjunction. Just observe that you can perfectly formulate this logic in one-sided sequence. We are not obliged to have a sequence with formulae on both sides. Cut is formulated this way. The cut formula is not the same in the two premises, but must be one must be the dual of the other. Okay. So this logic has, from a proof theoretical point of view, it has quite a lot of nice properties. It has maybe the only fragment of linear logic for which perfect system of proof nets exists. There is really a system of proof net which all the desirable properties. And cut-elimination obviously holds, and on top of that, cut-elimination has bounded complexity, for very simple reasons, because every cut-elimination steps makes the size of the proof smaller. And you can build, you can equip this logic with various forms of semantics, from coherent semantics to relational semantics to phase semantics, and all of them behave quite nicely. On the other hand, if you are interested in the expressive power of the logic from the point of view of the carry-over correspondence, it's quite poor. So the logic cannot represent, you cannot hope to represent functions with an infinite domain, for example, because the set of cut-free proofs for a given formula is finite. So there is nothing like Church numerals, say. Why? Because there is no duplication, no notion of duplication. Everything is treated in a purely linear way. On the other hand, if the computational model you are interested into is, let's say, finite itself, so if you take Boolean circuits, for example, you can find that there's a strong correspondence between circuits and MLL proofs. This has been investigated by Terui in a wonderful paper in 2004, which shows not only that all Boolean circuits can be encoded in MLL and vice versa, but also that the correspondence is quite tight. There are kind of precise correspondence between sets of MLL proofs and sets of functions computable by circuits with limited depth, for example. So the correspondence is quite deep and interesting. So let's just try to play with an example MLL proof to see one of the many nice properties the logic has. And let's, for example, let us focus on one occurrence of an atom in a conclusion. And just let's play the game of tracing the occurrence of this atom up in the proof until we reach an axiom. This is quite simple because the logic is absolutely is formulated in a very simple way. There is no occurrence of duplication, so you don't have any choice to make. You go up, and you reach the left axiom. And at this point, you can arguably do the choice of going on the other occurrence of the dual atom, and you go down until you reach the conclusion. So in some sense, even if this is a quite simple example, but this game can be played on all proofs, even if the same atom occurs many times at the conclusion, and even if cut is there. This proof is cut-free, but the same thing can be made also for cut-free, for proofs with cut, and the process terminates. So in some sense, this game allows you to put in correspondence an occurrence of an atom to an occurrence of the same atom in a dual version. And so proofs can be put in correspondences to matrices, which are symmetric and which are permutation matrices. So they are quite a restricted form of matrices. For example, in the case of this proof, the matrices just tell you that this atom corresponds to this coatom corresponds to this atom, etc. In this particular case, the proof, the matrix can be constructed by only looking at the conclusion, but it is not always the case, because the same atom can appear as many times. Okay.
So by constructing the matrices ourselves, or at least.
What I've just described you is a very primitive, maybe the simplest way of describing what is called the geometry of interaction of multiplicative linear logic. Actually, there are many different ways of presenting the same thing. Some of them are more complicated than others. There are, for example, even ways to present the geometry of interaction of multiplicative linear logic by using operator algebras or other more complicated mathematical descriptions. Here we are mainly interested in what I call an interaction abstract machine, which is exactly an automata theoretic way to compute this correspondence between occurrences of atom in the conclusion, which is exactly one of the ways to present the geometry of interaction. Other ways are the matrices, which is somehow the results of what I've just shown you. Actually, this is a way to give proofs a semantics, so it is invariant by cut-elimination. When you eliminate cuts inside the proof, the correspondence between atoms stays the same. And if you work with proofnet, you can even reconstruct the proofnet looking at the semantics. Actually, the cut-free version of a proof looking at its semantics. So why this can be helpful in the real mode of quantum computation? Let's go back to the example. In particular, let's go back to the matrix. And so the matrix we were talking about. Actually, this is a matrix which corresponds to an operator which is by definition invertible. The motivation, the question we posed ourselves with Claudia when we started doing this work was, what is missing in MLL to get exactly quantum computation restricted to, for example, pure quantum circuits? There is at least something which is missing. If you compute the geometry of interaction this way, all coefficients are either 0 or 1. And if you want to do quantum computation in the standard way, you need other complex numbers besides 0 and 1. So the idea we started from was the following. What if we replace this one coefficient linking one occurrence of an atom with the dual one with an operator? For example, a quantum gate, which can be, for example, the Hadamard gate. Clearly, if we put the Hadamard going from A bottom to A, you need the dual of the inverse of it when we go from A to A bottom, to keep everything reversible and uniform. The point is that the analogy with occurrences of atoms is somehow lost, because this is a 2 times 2 square matrix. So on the other hand, here we have just one occurrence of an atom. So what we can do is to kind of take the occurrence of the atom and split it into 2 copies, one corresponding to to one element of a base, and the other one corresponding to another element of the same base. What I'm going to show now is a small variation of multiplicative linear logic whose geometry of interaction is like this. Okay. What is that? It's really a straightforward variation on geometry of interaction, which is not obtained by endowing multiplicative linear logic with non-logical constants, but rather by keeping multiplicative linear logic with a form of modality, which is the modality you find here, box and diamond, which we call quantum box and quantum diamond. The 2 modalities are one dual of the other, and the only rule that we need to add to the system is this one, which is very much reminiscent of the K rule from modal logics. If you are able to conclude A, B, you can put n occurrences of diamond in front of A and n occurrences of box in front of B. It's crucial that this rule can be applied for every n. This is not this judgment is not the only premise of the rule. There's another premise which is quite essential. This is an operator on n qubits, or if you want, n qubit gate, a gate working on n qubits, which is, if you want, a unitary operator on C to the 2 to the n. Okay. Let's, before analyzing the geometry of interaction of this system, let's look at cut-elimination, just to be sure that cut-elimination continues to hold. So, okay, since you maybe don't know how to eliminate the multiplicative cuts, let's even look at that. If you face a cut involving multiplicative formulae, you just rearrange the 3 premises in such a way that the cut is lifted up, and is in particular now made and applied to smaller formulae. This is the same thing as in MLL. Okay. Now let's look at the most kind of interesting cut-elimination steps, the one for modal formulae. And there is one cut-elimination step that you do when the cut formulae is modal. And what you do here is to lift the cut, which from here goes to here. And you take the multiplication of the 2 matrices, if you want, or if you want the composition of the 2 operators as the underlying quantum operation. Okay. So cut elimination, in some sense, corresponds to composition of unitary operators, at least here. But what happens? To be able to eliminate all cuts, we need to be able to do some kind of, how to say, eta reduction, if you are familiar with the random calculus. If you have a modal, an instance of the modal rule followed by another instance of the modal rule, you can compress everything to one instance of the modal rule, in which the operator is not anymore the composition, but it's rather the tensor product. Then you can kind of equip the system with other cut-elimination rules, like the ones doing only some kind of commutation steps, And what you get is a relation which is confluent and strongly normalizing. Moreover, and this is the most important thing, the proofs which are normal with respect to this relation are cut-free. So you have an effective way to eliminate all cuts from this. So QMLL enjoys the cut elimination property. So let's now look at the correspondence between QMLL and quantum circuits. Why there is such a correspondence? And let's start from an example. Above here, you have a very simple quantum circuit, which, however, has almost all the, let's say, the necessary ingredients to be relevant. Let's say. So it has, let's say, 2 qubits. It works on 2 qubits. You do the other node on the first qubit in parallel with X on the other qubit, and then you do a C node. In particular, C node is relevant because you cannot decompose it into the tensor of two gates, unary gates. You can still play the game, that's the point. You can still play the game of following the occurrences of atoms up in the proof. But you cannot do the same thing as easily as in MLL anymore. Because you need, while you are traveling inside the proof, you need to have something to work on when you reach module formulas. And this is something is what? It's an element of, in this case, of C of the 2 to the 4. So a normalized vector in this space. And why is that? Why do you need exact, let's say, 2 qubits and not 4 qubits or 10 qubits? The number of qubits you need correspond exactly to the modal depth of the atom you are considering. If you start from an atom which is at depth 2, you need exactly 2 qubits. So let's go up. The last rule, okay, I have not written anything here, but it's we reach a model rule, and what you do here is to go up, but you somehow remember that you've entered the word of how to say the inner part of a model rule. You go up, and the occurrence of the atom is this. You go up and you reach an axiom. You go to the co-atom, and that's the crucial point. Here you are exiting from an instance of a model rule you have already visited. That's the point where you can apply the unitary operator which corresponds to the rule instance, to what? To, in this case, to the first qubit. Why? Because we just have one instance of the model rule here. So what you do here is to apply the Hadamard operator to the first qubit. Then we are again exiting from another model rule, but this time we are applying the X gate to the second qubit. So we do like that. So we are in a cut, so it's not we cannot go down anymore. We need to go to the other branch of the cut and go up. We reach the axiom, then we go down, and then we are exiting from another, say, modal rule, and we apply C node. And we are done. What I've just described informally can be clearly formalized appropriately, and the name we have kind of given to this machinery is the QIAM, which stands for the Quantum Interaction Abstract Machine. which is nothing more than a quantum variation of the interaction abstraction. And this is the reason why we claim that this logic has a correspondence to quantum, strong correspondence to quantum circuits. It's not cut-elimination that itself is a reversible machinery, but it's rather this interpretation by a geometry of interaction. Okay. What cut-elimination does is more like a transformation of quantum circuits which preserves their kind of overall behavior. So for example, you compose gates, or you just put, you just merge two gates which work on independent qubits into one. But this doesn't change if you want, it doesn't change the overall, the observable behavior of the quantum interactive abstract machine. Actually, we have proved that not only that all quantum circuits can be encoded into quantum multiplicative linear logical proof. And this is quite simple because as you follow the example, you can clearly put many weights and many qubits into play. But you can even prove that all proofs, even the ones containing cuts, correspond to one or more quantum circuits which work on separate sets of qubits. Every occurrence of an atom and the corresponding co-atom corresponds to one independent qubit in QMLL. So, summing up, we believe that this is first of all an interesting work because it's a purely logical account of quantum circuits. We don't need any non-logical constant or any non-logical, let's say, type in our system. And it's nice because there is also a GOI semantics for it, which it's not only useful, but it's necessary because the GOI is exactly what gives the system a truly quantum computational meaning. So this is not the first time somebody has worked on GOI related to quantum computation. There is a recent work by Aso and Shino on interpreting higher order quantum computation by GOI, and there is even work on proof nets in the context of quantum computation, which is done by Ross Duncan. In particular, our work is quite different from, I claim that our work is quite different from Duncan's one because we are very much interested in the micro behavior of qubits, while in Duncan's work the focus is on starting from a category of qubits and put some more structure over it. There's clearly some similarities with the CPM transformation, by the way, which needs to be investigated further. Clearly, this is not, as we presented it, it's not a satisfactory, let's say, quantum computational model by itself because we don't have any measurement, we don't have any way to let the quantum world and the classical world to interact with each other. So the next thing we are trying to do is precisely that. We need to extend the system in such a way that the quantum part and the classical part can interact in non-trivial ways. For example, by modeling some forms of measurement of the creation of qubits. And this maybe can take the form of a dereliction rule for the newly introduced modality. And we don't know yet what kind of category can correspond to this logic, at least up to now. Thank you.
Is it true to say that, in fact, you take a circuit, somehow you take the input and the output and you put it at the bottom, you take the gate and you put it as actions, and what you're saying in between is your proof, is the tree of the proof, or something like that?
Yeah, if you encode just one circuit, it's like that. The point is that not all proofs are like that, because you can have a proof, you can have proofs with many atoms, and you know, with many atoms, you don't have just one circuit, but you have many. In other words, what you've just described is the procedure of encoding arbitrary single quantum circuits into the logic. But if you want to do the other way around, let's say, starting from the logic, I understand what quantum circuit you have, there can be more than one. In particular, the procedure you are describing doesn't use any multiplicative connective at all. It's just, you know, cuts, actions, and modalities.
Okay, so okay, the second part of the question was, so is it possible to replace each rule of the thing by just a way to branch the wires? And it seems that it's,
more or less, yeah. Up to now, it's true. Why? Because the multiplicative part and the quantum part doesn't communicate. So everything commutes somehow. The multiplicative and the quantum part somehow commutes. From the point of view of the model, they commute. In the syntax, clearly not. There are no cut-elimination steps that allows you to let, let's say, a tensor node or an instance of the tensor root float down a modality. But in the semantics, that's true. Up to now, because if we, as we want to do, if we endow the system with some form of derivation, this is not anymore true. This is not relevant.
So, I possibly missed something in the presentation, but what would be a proof that corresponds to a quantum circuit with a crossing?
You mean, no, I understand. If you want to do the crossing, you need to put a quantum gate there, which we don't.
You don't have the crossing per se.
Yeah, no, we don't.
So you have only one proof essentially of diamond squared alpha, box squared alpha without using any gates.
Yeah. Yeah, true. If you use the quantum thing. Clearly, if you take the multiplicative thing, no. The multiplicative, clearly you can't do that. And this is one of the reasons why we want the two parts of the system to somehow communicate.
So, could you go back to your future work side?
Yeah.
So, on the, you know, to incorporate measurement, I guess you can replace all the unitary transformations in your framework into
True, I guess.
yeah, super operators or quantum operators.
But what we would like to, I think this way you cannot really turn the classical information that is encoded into the tensor and the par and the modality to really communicate. We would like, let's say, to have a single framework in which you have Terui's Boolean circuits, our quantum circuits, and all the interplay between them.
Right.
And we are working on that. We are actively working on that, but we believe that the right way to do that is a form of the dereliction rule, because the dereliction rule is exactly. This is quite inspired by, if you want, by another modality, which is the exponential modality of classical linear logic.